Hello! I've always been a fan of the Alien film franchise, even though the first film came out before I was even born. The way those films were put together created such an atmosphere of suspense and horror. Aliens, the sequel, was first released in 1986, and that one is my all-time favourite, especially the director's cut. But by far my most favourite thing in the film is the motion tracker they use. Not only the effect, but the heartbeat sound it makes while nothing is around, closely followed by the eerie noise it makes when something comes into range. So, here's one I built earlier, and with the release of the new Alien Earth series, this device has never been more useful. Now, many people have made replicas before, and most have just a little bit of a video playing just here, and none of these, as far as I know, actually work. Until now. This one actually works, not only making all the sounds, but it can also detect motion up to around 15 meters away, even through walls. And as you can see, it's detecting me right now, as you can see right on top of it. Nearly dropped it then. This is a project I've literally wanted to make for about 10 years ago since discovering the Arduino. So in this series of videos, I'm going to guide you through the design process, how the project evolved over the years, and how I ended up with this rather fantastic recreation. And if you don't want to miss the series, make sure you hit that subscribe button. The idea for this project came to me when I heard about these little radar modules. These little things can detect movement in the surrounding area, but unlike the usual normal passive infrared detectors, these ones can see through walls. It does this by sending out a radio signal at around 3.18 GHz, and then looking at the signal having been reflected by nearby objects. Once it stabilises to its surroundings, any movement causes it to trigger. Interestingly, this detects the disturbance using an almost identical chip to the ones typically found in those passive infrared detectors. We'll look into how these actually work later on, but this module sparked my interest. It couldn't tell you how far away the movement was, or even what direction, but I did have a little investigation, and I connected various pins to an oscilloscope and watched the signal change as I moved around. I'd hoped that maybe I could hook this up to a little Arduino with an LCD display and start building, but with so many other projects on, I put this one aside, until I stumbled across this little module. This one operated at 5.8 GHz and claimed to be able to detect motion up to 12 meters away. What's interesting to me is there were two variable resistors. One controls the duration of the detection of the pulse on the output pin, not really very interesting, but the other could change the detection range, and I wondered if I varied this somehow, then I could easily establish the distance between the sensor and the movement. Sadly, I never got to play with this, and it sat in a drawer for several years, until in 2023 I discovered this teeny tiny little radar module, the HLK LD2410. This runs at 24 GHz. The difference with this one though is it had a microprocessor on board, and it could actually tell you about objects nearby, moving nearby, and how far away they were, up to about 6 meters. The protocol was even published, so it's not really difficult to use either. I initially planned to connect this to an Arduino, although its UART speed is way beyond that processor. I did purchase some external UART chips that would have been perfect for this and communicated using the SPI bus. However, once again, I just didn't have the time. At the start of 2024, I started to look at this project again, and I discovered that that radar module had some siblings. This is the HLK LD2420. This operated at 24 GHz as well. However, this one can see up to 8 meters, and by this point, as the protocol was the same, there were many examples showing how to use it. I decided at this point that the Pi Pico would probably be a better fit for driving it, and I purchased an HDMI header so I could drive a nice LCD panel from it too. And then, time got in the way again. At the start of this year, I had the idea of mounting this in some kind of 3D printed gadget, and then using a servo to turn it left or right so we could get the angle as well as the distance. I even printed out a prototype, ready to test. See how the servo is mounted further back with a belt to drive it. This was to keep the electrical interference away from the sensor. I was even planning on adding a little accelerometer so I could detect that the person was holding the device was moving and then could compensate for it. And I was about to start working on this when an interesting email dropped in my inbox about a new radar module. This was the newly released DreamHAT RF hat for the Raspberry Pi. An interesting gadget, this one operates at 60 GHz and has up to 15 meters range. But what really excited me was this tiny little chip in the middle that did all the magic. This tiny little chip has one transmitter and 3 receivers, and what it did with those was entirely programmable. This is a small video from their website showing example apps that you could download. Looks interesting. And here's another one. This is almost exactly what I needed. So I ordered one of these boards, and well, these things aren't exactly cheap, which is why I'd like to give a shout out to my Patreon supporters, who make crazy projects like this possible, and I'd like to thank them for their support. If you'd like to support me, then head over to my Patreon page. Links are in the video description. And here it is. So let's take a quick look at what you get. And it comes in a nice box. Opening it up, and we find a few different things. This is the main module, and you can see the chip in the middle. When I get the angle right, you can just about make out the transmitter and receivers too. And you can see now that it simply clips onto the Raspberry Pi. The other accessories in the box are in case you want to clip this on top of a Raspberry Pi 5 whilst the cooling fan is connected. So that gets us up to date with radar modules, etc. So what happened next? Well, the first thing you do when you get a new gadget is to try out all the examples and get them running, and there's 4. 2 of them show you more raw data from the sensor. I'll explain a little bit about what these mean later, and you can see in this video that how the device responds to me moving around. And then there's this radar plot view, and you can sort of see how the dots follow the motion I make around the room. Perfect. I obviously need a way bigger room. Anyway, problem is that the chip on that board, the BGT60TR13C from Infineon, is a very well documented chip. In fact, the datasheet is massive and lots of scary maths inside it as well, most of which I don't even want to try and understand, but it's also very comprehensive. Like this diagram, this shows the precise distance between each of the radio antenna, and that distance is no mistake. This device operates at 60 GHz, and if you calculate the wavelength of the signal using this formula, and plugging in the numbers, including the speed of light, though that's an approximation to what we're told at school, you end up with 0.005 meters, or 5 millimeters. And those radio receivers are set 2.5 millimeters apart, which is exactly a half wavelength of the signal. Although I'm not going to go into too much science about why that's important. So anyway, this is all great if you're a maths or physics genius, which clearly I am not. So I started to look at the example code, written in Python. And whilst the examples are good, they're just not documented in a way that helped me to understand how they worked. I put the code to one side and started looking at the physical layout again. One of the things I wanted to do was mount this vertically, because you see, this chip actually senses in both the horizontal and vertical direction. That's why it has 3 receivers and not 2. Clipped to the Pi, the whole thing is just too wide to fit where I would like it to be, the handle of the device, which I'll come to later, whereas in a vertical direction it would just about squeeze in. In the H-plane, as the datasheet calls it, the sensor typically has a field of view around 40 degrees. Not bad, but in the vertical direction, or the E-plane, it increases to around 65. Now I thought this was an easy fix. I guessed that to work horizontally it would be using receiver 1 and 3, so all I would need to do is swap it to using receiver 2 and 3. Sounds easy, right? Well, it would have been if the examples hadn't been so misleading, including config files that did absolutely nothing and weren't related at all. I finally found out that I needed to use a special program called Radar Fusion GUI from Infineon that allows you to configure the chip with all of its registers, and I simply tick the change in the radio selection. However, after endless experimenting with this, I just couldn't get it to work as well as the horizontal direction. Sure, it was able to detect me, but it just wasn't as sensitive. I couldn't find any mention about this in the datasheet either, so I decided to somehow make it work in the horizontal plane. No problem, as you'll see later on in the design phase. I then spent ages going over the code trying to understand what it was doing. There were a few things to do with signal processing, one producing a fast Fourier transformation, or FFT. With audio, for example, this will tell you what frequencies are in a given sound. Another called Doppler, which makes sense and I'll explain why in a minute. And finally, one called DBF, which is digital beamforming, which is a way of projecting radio beams in different directions using interference. So how do these radar modules actually work? Well, there's a few things you need to understand before this will make sense. The first is called Doppler shift, and don't worry, it's much easier to understand than you think. A really good example of this is when you're standing still and a car goes by, especially one with a siren. Did you notice how the siren first sounded slightly higher pitch, and then as it passes you it seemed to get lower in pitch? Well, this is a trick used by all the radar modules to detect your speed. Imagine you're in a room, standing still, and you play a sound. Shortly, depending on the size of the room, you will hear that sound again as an echo as the sound bounces off a wall in front of you. If you measured the time between it being sent and bounced back, you could calculate the distance. If you were to measure the difference in frequency of the sound you send and the one received, they'd be identical. However, if you were moving backwards when you played the sound wave gets slightly stretched, so when the signal bounces back to you it's a slightly lower pitch, and you could detect that slight change in frequency. The same happens in reverse. If you move forward, the sound wave gets compressed and therefore increases its frequency. With a bit of math, you can look at the change in frequency to work out your speed relative to the wall, and how far away the wall is by measuring how long it takes for the sound to come back. This is how a lot of the radar detection systems work. Now you may have seen one of these little ultrasonic modules. One of these transmits and the other one receives, and the circuit measures the time delay between the two and calculates the distance. Interesting to note that measuring speed and distance only requires one receiving antenna, not two, and that brings us on to measuring the angle. Now, if you were in a room with your eyes shut, you still know what direction a sound is coming from. And you can do this because you have two ears, and likewise the sensor has two receivers. So how does this work? Well, once again like before, imagine you're in a room and someone is talking. If they're standing directly in front of you, both of your ears hear the sound identically. However, if they were standing to the side, one of your ears would actually hear them slightly earlier than the other, and your brain can work this out. With this chip, it sends out a known signal at 60 GHz, and then looks at the reflections in real time. Because the signal took slightly longer to reach one receiver versus the other, you'll notice that the position in the waveform received by each of the antenna is actually slightly different. They are out of phase with each other. This difference can be measured, and from that an angle can be calculated. Now, I don't understand all the maths behind that, and nor do I even want to. The theory is more than enough for me, and thankfully the code for this is already written. But it doesn't do exactly what I wanted it to do. Firstly, it only seems to have a range of around 7 meters, not the foretold 15 in the datasheet. Secondly, it only detects one movement at a time, not multiple. Needless to say, I had a lot of work to do. So I wanted to look at the hardware to use for this project, and aside from the radar and the Raspberry Pi boards, I knew I wanted some kind of LCD screen, some kind of battery supply, an accelerometer, and maybe a few other bits along the way. I finally found a 2.4-inch LCD module that communicated via the SPI bus and could easily connect to the Pi. Before connecting it, however, I needed to see what connections the radar module was actually using, given that it was plugged directly into the header. Turns out quite a few, and looking at the pin header, I now knew which pins to avoid. The radar module uses the SPI bus to communicate with the Raspberry Pi, and so does this LCD module. Now the Raspberry Pi can support two modules on the SPI bus by using these two pins here to select them. The problem is, this crappy LCD module doesn't have a chip select pin on it. So I need to make a fake one using some electronics instead. Not a deal breaker, but certainly annoying. How am I actually going to connect these while the radar module was connected? Well, that was a problem for later. I also knew I wanted some kind of trigger button to turn this on and off, rather than it running all the time. So I decided to use GPIO 21. That would be perfect for this. I also wanted to add an accelerometer, and that connects via the I2C bus, which isn't being used at all. Now, I chose to not worry about permanent connections for now, opting to do all the development whilst everything was connected to a breadboard. The screen can be supported directly by the Pi, although it's a little bit of a pain because of incompatibilities with later versions of the operating system, so I chose to control it from Python. I finally settled on the Luma LCD library, which didn't work out of the box either, and I had to use one of the versions that someone had left a pull request for. But once that was sorted, I was ready. Interestingly, this library also includes a screen simulator too, so you can test your code out without actually having the final screen connected. So this was my first experiment with the screen. I wanted something that would be useful later on, and well, those die-hard fans of Alien will instantly recognise the logo, and it's even on my t-shirt, look! The contrast on that screen is a lot better though, it's just the camera making it look a little washed out. Anyway, feeling confident, I moved on. This is all just basic drawing commands after all. Now after some research, I found some great examples of what the screen on the original tracker actually looked like. Firstly from this site, which was an excellent resource, but not only that, I saw this video featured. which showed the original prop used in the film. It's really interesting to see that the screen actually had a CRT tube sticking out the back and ran to some kind of video player. Anyway, we'll cover the casing later on. From these examples, I produced a rudimentary display looking like this. Just static, although the radar lines were actually calculated properly so I could rotate them later. The code also applied a slight blur to the lines because not only did the code not perform any anti-aliasing, but I also wanted to give it a slightly softened CRT appearance. With a little help from ChatGPT, I suddenly had a Python module that could read data from the accelerometer. I'm sure there's plenty out there that could do this already, but it was an interesting learning curve for me, and as you can see, as I rotate this board, the display changes too. However, that's actually rotating in the wrong direction, so a tiny little modification later and we get the desired result. I also implemented the code to make the radar pulse animation while the button was pressed. I was very excited at this point. Next up, I needed to plot the alien movement. My plan was to render circles and then heavily blur them. Each circle would be a specific distance and angle away from me. And I'm testing this here because this code just adds random ones every now and then, and it actually looks quite convincing. The code also allowed the alien movement marker to persist for a few seconds before gradually fading away. So that looks great, but one of the most important parts is sound. I knew that the sound was fairly basic, but I didn't want to include any sound files. I wanted them to be synthesized by the code in real time. Now, I knew the theory of what I wanted to do, but I'm lazy, so onto ChatGPT. I recorded a clip of the sound I wanted, cleaned it up and uploaded it. And I told it to analyse the sound, and from that extract the frequencies, phases and amplitudes of the detected sounds, and then write some code that could recreate this sound at any pitch I chose. I knew this was possible because any sound can be recreated by adding many different sine waves together, and after all, that's what an FFT will give you, more or less. Now this simulates a target getting closer and closer. And wow, the Raspberry Pi audio output is quite noisy. Ignoring that, however, you have to admit, that's really cool. Now, you already know that this fully works because you kinda saw it at the start, but there's still a lot left to do. There's getting the radar working and integrating it with the display and the sound. Then there's finding and refining a suitable 3D model that I did use to print this, from which then I had to house all the parts, and squeezing them in there really wasn't easy. There's a whole bunch of other things I've not even mentioned, including the fact that the LCD in here isn't even the one I was using before. So if you want to see how all of that was done, and get the links to everything, and even the source code, you better hit that subscribe button and don't forget that notification bell, because I'll show you in the next video, which will hopefully be along shortly. Anyway, I hope you found this interesting so far, watch out for them face huggers, and I'll see you in the next one.